looked at permutations, combinations, and the basic counting idea. They're pretty much the three main ideas. And when we've done the exercise as well, it's been fairly straightforward because this was an exercise on permutations, so we knew it was a permutation. This was an exercise on combinations, so we knew it was a combination. Now, in reality, when we look at a problem, we don't know. We're going to have to work out for ourselves. So just going to look at a few past questions. 2007, Mr. and Mrs. Roberts and their 4 children go to the theatre. Randomly allocated 6 adjacent seats in a single row. The probability that 4 children are allocated seats next to each other. So I guess the first question we have is it a permutation, is it a combination? Is order important in this one? In this case, it is, because of all the different ways they arrange, the order that they're sitting in could make a difference. We want seats that are next to each other. So there's the final probability, 3 factorial, 4 factorial over 6 factorial. How do we create that? Well, remember the bottom of the fraction would always be the number of ways of arranging the people, no restrictions. So 6 people we're arranging, 6 factorial. The top of the fraction, okay, so the 4 children wish to be in one group. There's 4 factorial ways they could be inside their one group. So that's what the 4 factorial is for. But then we have to arrange that group of 4 children plus another 2 people, the 2 adults. So that's 3 objects. It's 3 factorial. So that's where the 3 factorial comes from. And tidying that up, 1 in 5. 1 in 5 chance. How about we have a look at an extension 2? Because those of you who end up doing extension 2, there's this topic in extension 2 called harder extension 1. It's not actually a topic, but around about 25% of the final paper could actually be on extension 1 questions, but harder extension 1 questions. And they love asking permutations, combinations. So let's have a look at this one. Also from 2007. So a bag's got 12 red marbles, 12 yellow marbles. 6 marbles are selected at random without replacement. Now, without replacement is a key. Remember, if it's with replacement, then you can't use permutations and combinations idea. You've got to go back to the basic counting principle. But if it's without replacement, we can use permutations and combinations idea. We want the probability that exactly 3 of the marbles are red. Probability 3 are red. It's a combination in this case, because all I'm doing is drawing marbles out and getting a collection of marbles. The actual order that I draw them out doesn't matter. So here's how I've ended up. How did I get it? Well, again, the bottom of the fraction would have been total number of possibilities, no restrictions. So from the 24 marbles, we're going to choose 6 of them, so 24C6. On the top, I've got 12C3, because from the 12 red marbles, I want 3 of them to be red, because we said we want 3 of the marbles to be red. So 12C3, that leaves me with 3 left to go, so obviously the other 3 must be yellow. 12C3, and we come up with 0.36. Hence or otherwise, calculate the probability that more than 3 of the selected marbles are red. We know the probability for exactly 3 to be red is 0.36. So more than 3 red would be 4 are red, 5 are red, or 6 are red. There we go. Again, the bottom of the fraction is still 24C6. 4 red, well, from the 12, I'm going to choose 4. That means from the yellow, I'm going to choose 2. So 12C4, 12C2. 5 are red, 12C5, 5 from the red. 1 from the yellow, 12C1. And then all of them red, 12C6, and then 12C0. I'm going to choose none from the 12 yellow ones. And that all works out to be 0.32. 0.32. Another way you could have done this, because notice the question said, hence or otherwise. Now, I didn't really use part I. So I went or otherwise, if you like. But there must be a way of using part I, because I've said hence or otherwise. And here's the way of using part I. It's quite a clever little idea. If you had picked it up in the actual exam, it could have saved you some time. The probability of greater than 3 red, use the complementary events idea. So that'll be 1 minus the probability of, well, if it's not more than 3 red, what else could it be? Well, we've already worked out 3 red, so I could take that away. But then I'd also have to take away less than 3 red as well. But the probability of less than 3 red would be the same as the probability of greater 3 yellow. Because, I mean, it's the same thing. If I've got less than 3 red marbles, I must have more than 3 yellow marbles. But the drawing out of the marbles were actually equally likely. So the probability of more than 3 red is actually going to be the same as the probability of more than 3 yellow. So I could then rewrite my equation here. And so I could say 2 lots of the probability of more than 3 red is 1 minus the probability of 3 red, which I worked out in part I. And so we get half of 1 minus probability 3 red, and we come up with the same answer of 0.32. So quite a neat little way of doing it. I don't know how many people actually went that way, but it did say hence or otherwise, so of course the other way was certainly acceptable. But as I say, quite a neat little solution. Let's have a 2006 paper. Again, this is an extension 2 question. So it's a chess match, and there's the home team and the away team, very conveniently named. Games played on 4 boards, again conveniently named. Board 1, board 2, board 3 and board 4. On each board, the probability that the home team wins is 0.2, a draw is 0.6, and that the home team loses, or the away team wins, is 0.2. Okay, obviously it all adds up to probability 1. We record the results by listing the outcomes of the games for the home team in board order. So their example they've given us, if the home team wins on board, oh that should be board 1, shouldn't it? Home team wins on board 1, draws on board 2, loses on board 3, draws on board 4, we would record that result as WDLD. So it's the home team's result that we're recording. How many different recordings are possible? Well, I'm not worried about the probability of them happening here. It's just saying how many are possible. So on each board, there's 3 different events that could happen. Could win, lose, or draw. And that could happen on all 4 boards. So 3 by 3 by 3 by 3, 3 to the power of 4, 81. So what's the probability of getting the result that went win, draw, lose, draw? Because remember, they're not equally likely. So we're going to take probabilities into account now. So probability of that W was 0.2. We said probability of home team winning was 0.2. Probability of that draw, 0.6. Probability of the loss, 0.2. And probability of the draw, 0.6. So actually it's not 1 in 81. It works out to be 0.144. Now they add an extra bit to this game by allocating points. So a team will now score 1 point for a win, half a point for a draw, 0 points for a loss. The probability that the home team scores more points than the away team and so wins the overall tournament that they're playing. Okay. Well, the first thing I'm going to do is work out the probability that they score the same amount of points. How could they do that? Well, there could be 4 draws. A draw on each board, then they're going to score the same amount of points. That would be 0.6, 0.6, 0.6, 0.6, because the draw on all 4 boards, 0.1296. How else could they score equal points? 2 wins, 2 losses. If they both win 2 games and lose 2 games, they'll come up with an equal number of points. So 2 wins would be 0.2 squared. 2 losses would be 0.2 squared. But I've multiplied it by this 4 factorial on 2 factorial, 2 factorial. And the reason I've done that is there's different ways the events could happen. If I said, what's the probability of win, win, loss, loss? Yes, that would be 0.2 squared times 0.2 squared. But what happens if it was win, loss, win, loss? That would also be 0.2 squared times 0.2 squared. What happens if it's loss, loss, win, win? That would also be 0.2 squared. So the question is, how many ways can I arrange 2 W's and 2 L's? And it's like the question of how many words could I make? Well, we say, 4 factorial divided by the repetitions, 2 factorial, 2 factorial. Okay? So that 4 factorial, 2 factorial represents the number of ways of arranging the 2 wins and the 2 losses on the different boards. And there's another way. You can get 1 win, 1 loss, 2 draws. That would come up with the same number of points. So a win, a loss, 2 draws would go 0.2, 0.2, 0.6 squared. But again, How many ways can we arrange that? Win, loss, and 2 draws. Well, now it'll be 4 factorial on 2 factorial. It's like saying, how many words can you make out of, what would it be, W, L, and 2 Ds? So there are no other ways you could get equal points. So probability of equal points, add them all up, that's 0.312. So I now know or how many ways we can get the same number of points. But that's not the question. The question is, what's the probability the home team wins, scores more? Well, therefore, the probability that they're unequal points would be 1 minus the probability that they're equal points. So there's a 0.688 chance that the 2 teams finish on a different amount of points. But everything in this problem was equally likely. Remember, the chance of winning was the same as the chance of losing. So therefore, half of that 0.688 must be the situation where the home team scores more points, and the other half of that 0.688 must be when the away team scores more points. So half of our unequal points, there's our probability, 0.344. Quite an involved little question, but remember, as I say, this was an extension 2 question. This is like quite a difficult little problem. 2002 paper. Pack of 9 cards, just numbered 1 to 9. 3 cards drawn at random and laid on a table from left to right, and they're essentially forming a 3-digit number. What's the probability that that number exceeds 400? So even though you have got this harder question in extension 2, that doesn't mean every part of it's going to be difficult. This is a standard sort of question, isn't it? I mean, you've got numbers 1 to 9, probability exceeds 400. Well, probability exceeds 400 will be 6 out of 9. Because really, it's all to do with that first digit. And what's the probability that the first digit is more than 4? Well, 6 of those digits would be more than 4 out of the 9. So we're 2 and 3 chance. So that probably was the gift mark for that question. Part 2. What is the probability that the digits are drawn in descending order? Now, it doesn't mean it's consecutive. It might go 9, 6, 3. Or it might go 8, 7, 1. But the actual order is descending, is what they mean. Well, the total number of arrangements of 3 digits. There's 3 factorial different ways we could arrange the 3 digits. So the question is, how many of these ways would be in descending order? Okay. There'll be only one arrangement that's in descending order. Because what we're saying is, how many ways can we arrange the 3 digits? We've selected 3 digits. How many ways can we place them down so that they're in descending order? 1. It's only one way. So therefore the probability is 1 in 6. As I say, looking at some of those extension 2 ones gives you an idea of how difficult some of these problems can get at an extension 2 level. But of course we're dealing with extension 1 level this time. Some of those ones towards the end of the exercise can get quite involved. But we'll spend the rest of the time looking at some of our questions. So 10H is a mixture of perms and coms